All right, everyone, we're going to get started. Welcome to the latest webinar here on behalf of AMS Weather Band. This is winter weather, forecasting snow, and the challenges that come with it. Our speaker today is Kyle Elliott, who is the director for the Weather Information Center at Millersville University. I just want to go over a few ground rules. We are going to have a couple of times for answering questions. You will know at the end of each section when it is time to go to answering questions. I do ask that you stay muted throughout the presentation. And if you can ask questions at the end of the section, and especially using the Q&A function or the chat, I'll be monitoring that and relaying it to Kyle, which will be the easiest way to get our questions in. Kyle, on behalf of AMS and Weatherband, welcome and thank you for taking the time to speak with us today. I'll hand it over to you.
Thank you, Eric. I appreciate it. I'm really looking forward to the opportunity here. Today's presentation, I'm basically going to focus on different types of winter storms. I'll be focusing on Clipper systems, Arctic frontal systems, and then your classic Miller A and Miller B nor'easter type systems. And then I'll also hit on some impacts of snow, sleet, and freezing rain. Toward the end of the presentation, I'll go over a few forecasting tips for each of the different types of winter storms. And then I'll also discuss how you can predict and forecast differences between snow, sleet, and freezing rain from a very rather simplistic approach. So without further ado, I'm going to jump right in here. At the end of each section, I will take some time and ask if anybody has questions. So once I get to the end of Clippers, I'll pause and see if anybody has questions. The same with Arctic fronts and the same with Miller A and Miller B nor'easters. So I'll jump right in here. Clipper systems. What is a Clipper system and what is the large scale weather pattern where these systems generally form in? So oftentimes you'll see this big ridge in the jet stream over the western parts of the United States. So the jet stream bulges northward over the western US, and you have this broad trough or dip in the jet stream across central and eastern parts of the United States. I'm not sure how many are familiar with North Atlantic oscillation blocking or a negative NAO signal, but oftentimes when you have clippers, you actually won't have a negative NAO. So what that means is you'll have a very progressive weather pattern in parts of the eastern United States. Storm systems will be zipping along, moving hundreds of miles, even 1,000 miles in some cases or more, in a span of 24 hours or less due to that lack of blocking. What that blocking does is it slows down winter storms. And oftentimes when we see these clippers, we don't have any blocking. They're very fast moving, weak storm systems, and they generally track right along that dip in the jet stream, or where you see your tightest temperature gradient. Oftentimes you'll have much warmer conditions over the southeastern United States. And then just to the north of the Clipper track, you'll have much colder conditions in this Arctic air across northeastern parts of the US, southeastern Canada. And these systems tend to track right along where that gradient is most intense. By gradient, I mean a difference in temperature from south to north across the United States. Now, the difficulty with forecasting these Clipper systems is there's very rarely any accumulating snow along or south of the storm track. They're very weak and moisture starved to begin with. So north of the storm track is generally where you see this narrow 50 to 100 mile wide band of accumulating snowfall. So track means everything here with these clippers, because if they shift north 50 miles, well, the band of snow shifts north 50 miles. If they shift south 50 miles, there goes the band of snow 50 miles farther south than you would originally expect. So the exact track of them is very important. Now, because they're moisture-starved systems, these are not big snowstorms in most cases. Generally, they'll lay down a swath of between 1 to 3 or 3 to 6 inches of snow. Sometimes out here in the central parts of the US where you can have higher snow ratios, quite frequently, you may see some clippers put down between 6 and 8 inches of snow. But generally speaking, these are not big snowstorms, especially for the Ohio Valley and parts of the mid-Atlantic. So here's a historical track of some clippers. This is a total of 177 clippers from 1986 to the year 2000. So you can see most of these clippers actually track right along the northern tier of the US or even farther north in the United States across southeastern Canada. You have very few clipper storm tracks that actually track through the Ohio Valley or the Tennessee River Valley into the mid-Atlantic. Most of them actually stay right along the northern tier or affect parts of Canada. So you can see, like, generally speaking, the percentage of clippers that actually impact the United States, especially the eastern parts of the US, much less than the clippers that impact areas farther north. So a lot of what I'm going to be doing here today is basically attacking this from a historical perspective and going over different features that relate to the formation of these different systems. So the first historical example I want to go over here of a clipper system is January 22nd to the 23rd, 2005. Very famous example of a clipper system, and this one actually was one of the more robust clippers. And once it hit the east coast of the United States, this thing really intensified quickly. So this is kind of more of a rare case where you actually see the clipper system intensify more rapidly once it hits the east coast. So what you're looking at here is the jet stream level. So this is, some 30 to 35,000 feet above ground level here. You're looking at wind speeds here. The dark blue shaded areas are the wind speeds, and where you see these blue areas and brighter blue areas, such as over Maryland, Virginia, and North Carolina, that indicates much stronger wind speeds than in areas that you don't see shaded. So this narrow corridor of those stronger wind speeds, that's your jet stream. So that could be where you'd expect your clipper system. It would track right along this jet stream here from parts of the upper Midwest down through the Ohio Valley, and ultimately into the Mid-Atlantic and southern New England. And that's exactly where this clipper system tracked as well. They basically follow the jet stream. It guides their path, it guides their track in the end. So you can see the surface map here. There's that clipper system. This is a surface map for 2:47 p.m. on the 22nd of January, 2005. That clipper system, and I'll show you this in a radar loop in a bit, that clipper system entered the nation up here in North Dakota and Minnesota. It zipped southeastward really quickly, like I was saying, through the Ohio Valley, and ultimately exited the East Coast around New Jersey and then parts of southeastern New England. There you go, as we step forward in time, 11:29 p.m., January 22nd, 2005. Again, if I step back one, that's only about a 9-hour time period right there. And you can see how much ground that system has covered. It's moved from parts of Ohio well offshore of the Delmarva, New Jersey coastlines at this point. So this is not a slow-moving storm system. It's moving along very quickly. And another thing to note here is you can see your snowfall is north of the surface low pressure center track. Once you get along and south of that storm track, there's very little, if any, snowfall. And you can see that in the previous panel as well. That low is tracking across southern PA, off the Jersey coastline. Most of the heaviest snow is well to the north of the storm track. Now, again, this is a case of a stronger clipper system in comparison to most. So that's why you're seeing some snow here just along into the south of the storm track, because this system actually was in the process of redeveloping and transferring its energy off the Jersey coastline. Most times they won't do that. This was a stronger case, so it was attempting to do that. But as you can see, although it did do that, the snow, the heavier and steadier snow, was generally north of that clipper storm track. So here's the event radar loop. I want to show you this radar loop here really quickly. You can see just how fast that this system is moving. Everybody can see this?
I believe we're still on your on the slide presentation here.
Slide presentation. Let me see.
Oh.
It's showing me that I've got the radar loop up.
Okay, let's see. Paul
Unless
says he can. Let's see. Maybe it's just me. Let's see.
Share.
Okay. Yes, we can see the slideshow, but not the loop.
Not the loop. Okay, let me see what's going on here. I may have to stop sharing and then reshare. That's my guess. Yeah, here we go. All right, now you should be able to see the loop.
Yep, perfect.
Okay, great. Yeah, this is what I wanted to show you here. So this is the loop, the radar loop of that clipper system. This is a 24-hour loop right here of the radar. So you can see if the storm track was across Minnesota, Iowa, down here through the Ohio Valley, right along where I'm moving my cursor here. You can see that most of the heaviest precipitation was to the north of that. And look at just how fast this precipitation is moving. It's up in Minnesota. 24 hours later, it's snowing in Boston, Massachusetts. Nor'easters, especially Miller A's, they don't tend to move this quickly. So you can see just how fast these Clipper systems zip along. And because they're moving so quickly, it generally only snows for a period of 4 to 6 hours in any location with these Clippers. So you only have 4 to 6 hours in which you can see snowfall accumulation. And because of that, that's why it's so difficult to see high snowfall totals with these Clipper systems. So let me return to the presentation. All right. So then here what you see is a total snowfall accumulation from the January 22nd and 23rd, 2005 Clipper system. And you see generally what I was saying here. A large swath of 4 to 10 inches of snow, where the system did bomb out on the East Coast then and strengthen once it was able to hit those warmer waters of the Atlantic Ocean. There was some enhanced snowfall here in southeastern New England, parts of New York, but generally you can see the sharp cutoff here on the southern edge of that system, especially over parts of the Midwest and the Ohio Valley. If you're south of that storm track, you really didn't see much, if any, accumulating snowfall at all. And then just to the north of it, that's where you laid down your general swath of 4 to 10 inches of snow. And again, I'll stress one more time, keep in mind that this Clipper system was stronger than most. Most of them aren't this strong. So you will see a much narrow area of accumulating snow in most cases with these Clipper systems. So here's a couple of forecasting tips and challenges for Clippers. Again, they're typically weak, fast-moving systems that are starved for moisture. They're driven by large north to south temperature changes, and the bigger the difference, typically the stronger the Clipper system and the heavier the snow to the north of its track. Accumulating snow, again, it's typically falling in a 50 to 100 mile wide band. So the exact track of the storm basically means everything here. Oftentimes these Clipper systems, if you recall from the historical tracks, they'll actually track farther north in the eastern United States. So they'll track over New York State, parts of southeastern Canada. So if you're in the big cities of the I-95 corridor, oftentimes the snow struggles to get east of the Appalachians. That's because around a low pressure system, you have a counterclockwise flow of air, such that to the south of the storm track, your winds will be westerly. And if your winds are westerly, they're coming up and over the Appalachian Mountains, and then they, what we call as forecasters, downslope into the major cities of the I-95 corridor. And when you have downsloping winds, that oftentimes kills the precipitation. It dries out the atmosphere, temperatures warm up, and the precipitation never, in fact, makes it to the east of the Appalachians, as it, in essence, dries up over the mountains due to that downsloping flow to their east. So that's all I have for Clipper systems. I'll take the first round of questions on Clippers.
Great, thanks so much. So the first question we have here comes from James, who writes, since Clipper snow has a higher fluff factor, snow-water ratio, the snow tends to blow more easily, but is lighter to shovel. Should ratios be part of snowfall forecast since it does affect impact?
Yes, absolutely. We as forecasters oftentimes will look at snowfall ratios. In fact, we always do. Typically, if your surface temperatures are in the low to mid 30s during a snowfall, you would expect lower snow to liquid ratios. So again, if your temperatures are between 30 and 35, I'm thinking more often than not, snow liquid ratios on the order of 8 to 12 inches of snow for every 1 inch of liquid equivalent precipitation. If your temperatures are in the teens or the 20s, that's when your snow ratios can really go up, on the order of 12 to 20 to 1. In the most extreme cases, they can exceed 20 to 1, especially here over parts of the central and northern plains. You can oftentimes get bitterly cold air masses settling in those areas that these Clippers interact with. So in those cases, I've seen snow ratios as high as 30 to 1 in parts of the central and northern plains. And in those cases, like you said, snow will tend to blow and drift more easily just based on how dry it is. It's not going to compact on itself. It's not going to compress. So you get this blowing and drifting of snow if you have winds on the order of 10 to 20 miles per hour or more. So oftentimes in the wake of these systems, especially in the central plains, if it does become windy in their wake, you oftentimes get what we call ground blizzards, or where you're driving along the highway, visibility might be 10 plus miles, you hit a gust of wind, it's blowing this snow across the highway and your visibility goes from 10 miles to a quarter mile or less in a matter of feet in some instances. So yes, snow ratios are very important when forecasting.
All right, we've got a hand raised here from Pierre.
Yeah, can you hear me?
Yeah, Yep, I can hear you.
I was wondering what actually causes the Clipper to form there over the, looks like they form mostly over BC in Canada. And
Right.
yeah, there doesn't seem to be a big synoptic setup for it there. By that, I mean, there's no trough, which you would normally expect for a storm to form.
Right. Yeah, I can answer that for you. Oftentimes what will happen is, I kind of showed it on the first slide where you have that big ridge in the west, but keep in mind, oftentimes when you do have that ridge in the west, disturbances will come way up over the top of the ridge. So in the image that I showed you, you wouldn't even see where the disturbance originates. Oftentimes it'll originate in far northwestern British Columbia, sometimes up in Alaska, and these little pieces of energy will ride over the top of the ridge. So the low pressure will actually, we say it originates in Alberta, but in reality, oftentimes they'll originate much farther to the north and west. As these pieces of energy come over the top of that ridge, then we oftentimes see those storm systems come down into Alberta and zip across parts of the central US. But in reality, they are impacting areas farther north and west. It's just oftentimes we don't, pay attention to them until they get into Alberta or the northern parts of the US.
So they're really short waves, very short waves.
Yes, they're very much shortwave disturbances, not very strong pockets of vorticity, if you want to call it that. Again, vorticity is generally like a broad scale rotation, a measure of broad scale rotation within the atmosphere. So you'd have a very small pocket of cyclonic vorticity with these clippers.
Right. Okay. Thank you.
Yeah, you got it.
All right, we have another question coming in from Bruce. Bruce asks, can you speak to cases where an upper trough amplifies dramatically and a clipper transitions into an East Coast low nor'easter?
You kind of see that in this case, believe it or not, the 22nd and 23rd of January 2005. That system hits the coast. I actually took out a lot of the 500 millibar maps that I had in a more technical version of this presentation. So if I did have those maps in there, I'd show you what happens. Oftentimes, when they do amplify on the East Coast, you have a very amplified trough ridge pattern, kind of like what you see in that case, January 22nd and 23rd. Because the ridge axis is so far north in the west, the disturbance drops almost straight north to south throughout parts of the central and midwestern US, such that by the time the system hits the East Coast, that trough axis is already starting to go negatively tilted. What I mean by that is negatively tilted when it hits the East Coast. The axis of the trough is oriented from northwest to southeast. When they're positively tilted, generally speaking, in the north, in the United States, they'll be oriented from northeast to southwest. But when you have this major amplification in the jet stream, they'll be able to round the base of that jet stream and then take on that negative tilt. And when they take on that negative tilt, that helps the storm systems bomb out. So that's really the key, just basically judging how strong that ridge trough couplet is from the western to eastern parts of the US.
All right, thanks. So if we have time for one more question, I've got one from Gordon.
Sure. Okay.
So Gordon asks, models tend to overestimate QPE often, it seems to me, with clippers. Would you agree, speaking in terms of North Central and Midwest United States?
That's a tricky question. It's really reliant on the setup. Oftentimes they will overdo the QPF itself, but they oftentimes underdo the snowfall ratios, is something I've noticed for the Midwestern and northern parts of the US. And I'm not exactly sure why that is, other than the fact that these clipper systems are moisture starved. Keep in mind, they're diving down from Alberta, Canada. They're not tapping into Great Lakes moisture. They're not tapping into Gulf of Mexico moisture or Atlantic moisture until they reach at least the Ohio Valley or really hit the east coast of the US. So I think what you see with models here is, models do very poorly with quantitative precipitation forecasts in comparison to how they do with upper level forecasts. So oftentimes you have to take into account how strong is that shortwave disturbance that's actually spawning the clipper system. And then you also have to take into account its origin and what historically you typically find with these systems. And again, that's where we as forecasters come in, knowing the strengths and the weaknesses of each individual model. So again, it can vary from case to case, but yeah, it doesn't surprise me that models would generally overdo QPF in the central US with clippers. But at the end of the day, sometimes if you're just looking at QPF, it doesn't always matter if they've overdone it if you're taking those snowfall ratios into account. Because if you do take the ratios into account and you're just looking at a 10-to-1 or a 12-to-1 snowfall output map, oftentimes you'll actually see the same thing work out because the QPF's less, but the ratios are higher. If that answers your question. Now, again, looking back on as a forecaster, I would try to take both into account. Sometimes you may just consider that getting lucky. If you're like, oh, well, we're predicting 6 to 10 inches of snow from this clipper. Models were overdone and you're using like a 10-to-1 snowfall ratio. Well, you might get lucky if the models are overdone on QPF, because if you're using a 10-to-1 ratio, maybe the ratio is actually 20-to-1, but that's not a good principle to take in forecasting. Usually you want to take into account the strengths and the weaknesses of the models, take into account those snow ratios, and then adjust your forecast accordingly to those known biases of the models and how these systems have behaved in the past events.
All right, great, thank you.
Yep. Any more questions that we have time for?
Thanks. I think we got time to move on to the next section. Yep.
Okay, sounds good, Eric. All right, so the next section is going to be Arctic fronts. Arctic fronts are very challenging to forecast. It's very difficult to pinpoint any potential smaller snow squalls or snow bands associated with these fronts until about 24 to 36 hours in advance. So now these Arctic fronts are not going to produce big snowstorms. And again, when I mention Arctic front, I'm focused on just the snowfall that occurs from the frontal system alone, not with the low pressure system farther north. So with these Arctic fronts, oftentimes you will see a primer front or an initial front that basically brings in an air mass cold enough for the snow to fall. And you see that here in this case. You see this initial front to the south and east of Florida. Look at the temperatures out ahead of that front. You see temperatures ahead of that 68, 75 down there over the Bahamas. In the wake of that front, look at your temperatures in the Carolinas. They're in the 20s, they're in the 30s. That's cold enough for snow. New York City, it's difficult to see, but that's 24 degrees Fahrenheit. So it's more than cold enough to snow in this case. The Arctic front oftentimes occurs as a second frontal boundary that's bringing in your true Arctic air mass. So look at the temperatures in the wake of that Arctic front. You see temperatures -5 degrees around Detroit, near where my black arrow is there on the map. 19 degrees in parts of Kentucky, 14 over parts of Illinois. So there's another big decline in temperature in the wake of these Arctic frontal boundaries. And oftentimes these Arctic fronts will be associated with a narrow, very heavy band of snowfall as they come through, what we typically call a snow squall. So I'll move on to the next slide here. You got to think in sorts of a squall line mentality. This is about as deep into the weeds as I'll get with meteorology here. This is a schematic generally showing how snow squalls form along these Arctic boundaries. So you have very strong winds aloft. There's no directional wind shear. What I mean by wind shear is a change in wind speed or direction with height. You're not really going to see a change with wind direction with height in this case of these Arctic fronts. Now, what you may see is a strong change in wind speed with height. So you have speed shear, but you don't have directional shear. And you'll see that oftentimes associated with squall line cases in the summertime as well. You have a lot of speed shear, but you don't have a lot of directional shear associated with these stronger what we call quasi-linear convective systems, or in layman's terms, squall lines. So in these Arctic frontal cases, the strength of the Arctic front is very important, since the low-level convergence along the boundary plays a key role in driving the squall formation. So you can see the leading edge. Oh, wow, what happened? What you can see here is the leading edge of the frontal boundary right there. Arctic air in its wake, more seasonably cold air out ahead of it. You have convergence right along that frontal boundary, and where you have that surface convergence, you have very strong lift. If air is moving toward each other, what we call convergence as meteorologists, wind direction on one side of the front will be different than it is in the wake of that frontal boundary. So pretend you have south or southeasterly flow ahead of that boundary coming in from the right side of the page, meeting with that westerly flow coming in from the left side of the page. That air is combined, it's coming together. And when air comes together or converges, it's got nowhere to go but up. It obviously can't go down since it can't go into the ground. So it's got to go up. And the stronger the frontal boundary, the stronger that convergence, the stronger the lift. And the stronger the lift, the heavier the snow squalls and the heavier the precipitation. So again, a larger temperature difference on either side of that Arctic front means that in general, the front is stronger. So if you have a very big difference in temperature from one side of the front to the other, you'll get that stronger convergence along the front, and you could expect to see heavier snow squalls associated with that Arctic frontal boundary. So this is my historical case here. This is from January 30th, 2019. You can see from the radar imagery here, that squall right there is associated with an Arctic frontal boundary. So you can see it's a very narrow band of extremely heavy snowfall rates. These squalls typically last anywhere from 15 to 45 minutes as the Arctic front moves through. But the issue with these Arctic fronts, it's the impacts to travel. That's the really biggest concern with these frontal boundaries. You don't have much lead time with these Arctic fronts. A lot of times you won't even know if they're going to happen, these snow squalls associated with them, until about 24 hours before the front arrives. And even then, it's very difficult to predict the exact timing of these squalls in any given location. That's why you see the National Weather Service, they'll only issue these snow squall warnings at most 30 to 60 minutes before the snow squall moves through your location, because they're very difficult to time, and their intensity oftentimes fluctuates too, depending on where the snow squall is located, over higher terrain or over lower terrain. So you're not going to get much advance notice with these squalls. And when people are traveling along these major interstates, they're not, they could be traveling on a partly sunny day. They see this, what looks like a white or a bright look in the sky ahead of them, and they're thinking, oh, it's just a snow flurry. When in reality, it's a snow squall that'll reduce roadway visibility from 10 miles to near zero. It's a virtual whiteout in some of these squalls. So you'll go from 10-mile visibility to 0-mile visibility in the snap of a finger, in a matter of a couple hundred feet. And that's a very dangerous situation, because you just can't see the car in front of you at that point. Your visibility is limited to several hundred feet, and it's very difficult to see the next person in front of you. Not to mention, roadways can go from dry to snow-covered and slippery within a matter of minutes in these squalls. So if people don't slow down in time, they spin out or slip out on the highways. There's a multi-car pileup and a very significant, and in some cases, life-threatening accidents. So that's the real issues with these snow squalls, the impacts that they have on travel. And oftentimes you'll see this occur on Interstate 80 across northern PA. It's a very tough road when it comes to traveling through these snow squalls, because these squalls tend to impact Interstate 80 very frequently in the winter times, especially in colder winters when you have more Arctic fronts moving through the central and northeastern United States. You'll hear of multi-car vehicle accidents, 50-plus car pileups on Interstate 80 when these squalls come through, because you just don't have a lot of advance notice and people aren't ready for them. So they're very hazardous. In fact, one of the most hazardous forms of snowfall when it comes to impacts to travel in the wintertime, just based on the fact we cannot give much lead time for these snow squalls. A couple more challenges with these Arctic fronts. Radars aren't much use when trying to determine the intensity of the snow squalls. And I'll explain why. Oftentimes you'll see these snow squalls pulse up, or they look more intense near the site of a radar. For instance, if a snow squall is moving through State College, PA, as it gets closer to the radar, it'll look like it's intensifying. It'll look like it's the strongest when it moves over the radar site. Then once it moves away from the radar site, it'll give this impression that it's losing its intensity again. In reality, that's not actually happening. The reason that the radar beam will actually show less intense snow the farther away from the radar you go is because radar beams, they don't go out on a flat surface. They're pointed, they're angled upward. So a radar beam is angled upward slightly from the surface. So the farther away you get from the radar, the higher up in the sky you're actually looking. So these squalls are very shallow phenomena. The top of these squalls, unlike summer thunderstorms, these squalls in wintertime are only about 7,000 to 10,000 feet high, whereas a typical summer thunderstorm can go 40 to 50,000 feet. These squalls are shallow, so the radar beam oftentimes shoots right above the snow squall. Doesn't even see it once the squall gets 50 to 100 miles away from a radar site. So that's why it gives this false impression that the squall is pulsing in intensity, when in reality, in all likelihood, in many cases, it's staying just as intense, even though the radar suggests that it isn't. So what we'll see, like I said, is these dramatic changes in radar appearance or radar reflectivity over time. Brighter, heavier snow returns near the radar site, and dimmer, lighter returns farther from the radar site. So how do we as forecasters solve this dilemma? One way in which we can do this is to turn to satellite imagery. The satellite imagery is going to show the exact intensity of these snow squalls, and you won't actually see this pulsation where the squall weakens, this pseudo presentation where the squall weakens and strengthens. You'll see this very thin band of a bubbly presentation on the satellite. So if you look at my slide here on the far right of the slide, you can almost see over Lake Michigan and Lake Superior there. You see that very narrow band where you've got these bubbly appearances. That's, in this case, this is lake effect snow, but you can see the same thing on satellite in these Arctic frontal cases. You'll see these very thin bands where the clouds have this bubbly appearance, indicating an unstable lower part of the atmosphere and significant convection by wintertime standards. So oftentimes I will use the satellite imagery to help guide me with whether or not these squalls actually are gaining or losing strength. Another tool that is absolutely invaluable when forecasting snow squalls, checking traffic cameras. Many states will have the departments of transportation have their respective websites where you'll have access to all different types of traffic cams in different locations across the state. So I utilize this in the case of Arctic fronts. When I see the snow squall over a given location and there's a traffic camera there, pull up the image from the traffic camera. If you can't see anything on the traffic camera, you know the squall is really intense. Whereas if you pull up the traffic camera and you can see a pretty good ways on the camera and it looks like visibility several miles, well, maybe the squall isn't that intense as it's moving through that location. So don't underestimate the value of traffic cameras when you're trying to forecast intensity of snow squalls. So I'll just briefly go over this. Here's a picture, and this was actually from January 30th of 2019. Look at that multi-vehicle crash. Cars spun off the road. Down in ditches, multi-vehicle pile up here. You've got ambulances, fire trucks, police vehicles out because, 30, 40, 50 vehicles are involved in an accident here because they're not ready for it. Short-lived band of heavy snow, 15 to 45 minutes. Your roadway visibilities are going from 10 miles to near zero in a matter of a few minutes or even seconds in some cases. And again, these squalls can dump 1 to 2 inches of snow in just 15 to 45 minutes. They're very short-lived but dynamic systems, much like summertime squall lines. So you'll see this 1 to 2 inches of snow fall on roadways, and that's enough to cause icy roadways and treacherous accidents. So if people are going along, here's the other issue. When people run into these snow squalls, they'll tend to jam on their brakes. That's not what you want to do. You want to slow down gradually. You want to gently pump the brakes. You never want to slam on the brakes if you feel your car sliding out. Take it easy, try to remain calm, and just pump the brakes gently or gradually slow down. And a lot of times people panic when they run into these snow squalls and you have everybody jamming on their brakes. The brakes are not going to get traction when you have these icy roadway conditions. And there you go. There's your multi-vehicle pileup. So that's really the challenge with Arctic frontal systems. So I'll stop there for the next round of questions.
All right, great. Thanks, Kyle.
Yeah, of course.
I will be scanning the chat. For those of you in New England, we actually just experienced a squall, I think just last week, running through. That was very, very drastic to see. Yeah.
How hard were you hit up there?
Well, central Massachusetts it kind of cooled off as it went closer to Boston, but it was very interesting because not even just shortly before it was perfectly fine, clear conditions, and then white out. And then
right. Yeah, that's the same thing that happened. I know what you're talking about because we had the same thing down here at Millersville. The squall here at Millersville itself was actually unimpressive, but areas just to our north and west. I mean, I was watching traffic cameras. The sun's out. It's 40 degrees. Pull up the traffic camera a couple minutes later, you can't see anything on the camera. It literally looks like a wall of white or a snow hurricane coming in.
All right, we have a question here from Bruce, who asks, it would seem that to the lee of the Great Lakes, lake moisture would enhance these types of Arctic frontal snow squall events. Is that true?
It oftentimes will. And we actually almost saw that the other day a little bit. That snow, it'll give added moisture because, again, keep in mind, in the wake of these Arctic fronts, you'll typically have north or northwesterly flow. So if the Great Lakes are open for business, that's the key. You got to see if the Great Lakes are ice covered or not. Oftentimes when the Great Lakes are ice covered, then obviously you can't tap into the moisture that would otherwise be available from the lakes. But if the lakes are open for business, absolutely. Northwesterly flow in the wake of the front, you're picking up some of that moisture from the lakes and you're enhancing it into the back of that snow squall, in essence. So you're throwing it into the back of that squall. Oftentimes you also see a stronger temperature gradient too in those cases. Depending, again, that depends on if the lakes are open for business and if the lake water, how cold or warm those lake waters are. If the lake waters are too warm, then you may actually decrease that temperature gradient because you're blowing that northwesterly flow over the warmer lake waters. But usually when those lakes are cold, 33, 36, 37 degrees, that's pretty ideal in that case because you're not going to lessen the temperature gradient, but at the same time, the lakes are still open for business. So you can pick up moisture from the Great Lakes.
All right, thanks for that answer.
Yeah, absolutely.
Got another question from Lillian, who asks, are intense hailstorms in summer on the beaches of LI squalls?
That's a very general question. Usually in the, I can't speak to that one way or another. Summertime thunderstorms can form in a multitude of different synoptic and large scale setups. The dynamics, again, that typically lead to a hailstorm, oftentimes in squall line situations, straight line winds will be your primary mode of severe weather and not hail. I'm not saying it can't happen, obviously, but typically more times than not in squall line cases or what we call derechos, you'll see straight line wind damage being the most significant mode of severe weather. So more times than not, I would guess that a hailstorm on the coast would be a different setup than what we're talking about here with these Arctic frontal boundaries and severe squall lines in the summer.
All right, great, thanks. I think we got time for one more question if someone would like to ask in the Q&A. And if not, we can go to the third section.
Okay.
Right,
Sounds
thanks.
good. Yeah, no problem. All right, I'll move right along here. I hope everybody's ready for the fun stuff. Miller A's and Miller B's. Here we go, the big ones. So now we're going to talk about nor'easters and the two different types. So there's a Miller A type and a Miller B type. Oftentimes, they're just general terms to describe the behavior of these storm systems. A Miller A system, oftentimes you'll see one area of low pressure develop in the south central United States or in the Gulf of Mexico, and it remains one single low pressure system as it tracks the whole way up the east coast of the United States. There's no transfer of energy from one part of the country to another. It's just one singular area of low pressure that oftentimes bombs out as it moves up the east coast. Miller B's are a little bit different. Oftentimes you'll see one area of low pressure tracking across the central parts of the US into the Ohio Valley, but that'll tend to weaken as it gets toward the Appalachians and what we as forecasters call transfer its moisture toward the East Coast. That's exactly what Miller B's do. So oftentimes you'll have a disturbance that's moving into the Ohio Valley, and that disturbance is weakening as it does so, but there will be another disturbance more times than not, often to the south and west of that, that'll round the base of the trough that's present in the eastern US, and then that'll become the primary disturbance, such that you see the surface low pressure system in the Ohio Valley weaken and a new one form on the East Coast, and that's the one that becomes dominant and takes over. In both cases, you can get major snowstorms along the East Coast, and I will show you two very classic, well-known examples of a Miller B and a Miller A, both of which produced historic storms in the I-95 corridor, much of the mid-Atlantic and the Northeast. First one is the big one, the Miller A example from January of 1996. I'm sure everybody remembers this storm system. This is kind of like the benchmark for all mid-Atlantic and Northeast winter storms. The blizzard in January of 2016, 20 years later, it was very similar. The upper level charts and the radar, the surface charts, they all looked very similar to one another. The two storms were almost like a mirror image of one another. So I think back in 2016, you heard a lot of forecasters comparing that upcoming system to the January 1996 blizzard, and rightfully so, because they both had very similar looks. So if you take a look at this map here, this is an upper level map. So this is a 500 millibar height, wind speed, and absolute vorticity map. I know it all sounds very complicated, and I'm not going to dive into the weeds of what all those different terms mean, but note the areas here where you see the yellow, bronze, and gold shading. That's what we as forecasters call vorticity. Again, that's simply a measure of the spin or large-scale spin and rotation in the atmosphere. So where you see these enhanced pockets of vorticity, in this case over Oklahoma, parts of the deep south, there in southwestern parts of the Ohio Valley, they're just simply pieces of energy. Think of it as pieces of energy supporting the surface low pressure system. That's how I oftentimes describe vorticity. It's just the energy and the disturbance aloft that's supporting the surface cyclone. So you can see here in January 96, look at how deep the trough is in the central and eastern parts of the United States. You've already got a closed 500 millibar height contour. That's very key. Oftentimes in these strengthening, deepening nor'easters, you'll start seeing these contours. The contours meaning the dark black lines on this screen, they'll start closing off at 500 millibars. That is a sign of a rapidly deepening upper level shortwave. And with respect to that, oftentimes when the upper level shortwave deepens, you'll see the surface low pressure system deepen, snowfall rates increase, and become more intense. And that's exactly what you see here in January of 96. Why does this keep happening? Give me 2 seconds to try to fix this issue with the presentation. There we go. All right, so pay attention on this map to this piece of energy here over Oklahoma, and then this other piece of energy down over the deep south. Look, well, I'll get to that, but look, actually I'll do that here. Look what happens as we step forward in time. So compare these two maps. You see this other shortwave kind of rounding the base of the trough over Oklahoma and the other one down over the deep south. If I step forward 2 time frames there, you see that now those 2 disturbances are linked up. So when these pieces of energy phase or combine forces, that's oftentimes when you see these systems bomb out. And take a look at how many closed contours we have at 500 millibars now in comparison to a few hours earlier. This is a 12-hour time step here. So this is 12Z on January 7th, 1996. This is 0Z on January 8th. 2 more contours have closed at 500 millibars just in that 12-hour window. So that's the sign of a very rapidly deepening winter storm. Let me go back to the surface chart here. And what you see here on the surface chart is you see one area of low pressure. This was a Miller A. So you had one area of low pressure develop in the deep south, track northeastward into eastern parts of South Carolina, and look at what's going on to the north of that. You've got this incredible fetch of moisture from the Atlantic Ocean being drawn into the mid-Atlantic states, into the central Appalachians, and all that moisture is being dragged up into the cold air and falling in the form of heavy snow. So again, stepping forward 12 hours, you see this system strengthening as these contours close off at 500 millibars. And look at what happens to your surface cyclone. It's bombed out at this point. It is rapidly deepened here by late in the evening on January 7th. And look at that snow band that you have over southeastern PA. Oftentimes, there's something that we call a deformation band that develops on the northwest side of these nor'easters. That's basically where all that warm, moist air from the Atlantic Ocean gets transported to the north and western flanks of these systems. Oftentimes, you'll see the deformation band about 100 to 150 miles to the north and west of the surface low pressure track. And where that deformation band sets up is where all that moisture is being transported and then deposited in the form of heavy snow. And as these systems slow down, those deformation bands or those heavy bands of snow will oftentimes just sit over, a 50 to 100 mile wide location for hours and hours on end. This is how you get your 2 to 4 inch per hour snowfall rates in your nor'easters, a rapidly intensifying storm system that has a strong deformation band on its northern and western flanks. Look at what happens here as we step forward 12 more hours. By the morning of January 8th, now you've still got 3 closed height contours at 500 millibars, but the storm system's deepened. Our first closed contour was 534, which is that. I want to explain what the numbers on this map mean. This means that the level of the 500 millibar pressure surface, we're on a constant pressure surface here on these maps. That 534 represents the height of that 500 millibar surface above the ground in decameters. So where you see that 534, that means the level of the 500 millibar pressure surface is 5,340 meters above the ground. That's all those numbers mean on the map there, the dark black numbers. So what you see here is all of a sudden, our first closed contour was 534 decameters. Now we're down to 522 decameters. That means you're ramming cold air in the backside of this trough, in the backside of the storm system. The storm system, because it's deepening, is pulling warmer air up out ahead of the storm itself on its eastern flank. So you're enhancing this trough ridge system. And the system is basically undergoing rapid cyclogenesis at that point, or a self-development process, because as the upper level disturbance strengthens, the surface cyclone strengthens. And as that happens, your pattern of warm air being brought northward on its eastern side is accentuated, just as your pattern of bringing cold air southward on its western side is accentuated. So you're strengthening the temperature gradient or difference in temperature from one side of the system to another. So again, it's that self-development type of process that really leads to the strengthening of these maturing nor'easters. So again, here's 12Z on January 8th at this point. What you're looking at here is the system that's reached maturity. Oftentimes, one other thing I want to point out is you'll oftentimes want to see your surface low pressure system stay out in advance of where you see these closed contours at 500 millibars, because think of it as that's your center of your storm system higher up in the atmosphere. You don't want to see these two get on top of one another, because once the center of the upper level storm gets above the center of the low level of the surface cyclone, the system starts to unwind and it starts to weaken, because you can't have rising motion throughout all parts of the atmosphere. The storm needs to ventilate, meaning that if you have convergence at the surface, you need to have divergence in the upper levels of the atmosphere. And if you have a surface low directly beneath a mid and an upper level low, well, you're having convergence in the mid levels, you're having convergence in the low levels. At some point, there's got to be sinking motion somewhere in between there. So once that process happens, the cyclone has reached maturity, and it will begin to weaken thereafter. So take a look at this. In these impressive nor'easters, historic nor'easters in this case, you can get just monumental snowfall amounts. And that's exactly what we had here in January 1996. We had this Arctic air mass in place. If I go back one frame or a couple frames here, see that big area of high pressure system that's located north of New York State? You'll oftentimes see that in the case of nor'easters. That high pressure system helps funnel cold air down through New England into the mid-Atlantic. And when those high pressure systems don't give up their ground and they kind of stay in place as the storm system's coming up the coast, it'll keep that source and supply of cold air coming southward through the Northeast into the mid-Atlantic. So we won't have to deal with snow changing over to sleet or freezing rain. All the precipitation just falls as snow. So the position of that high and the strength of that high is very critical. And that there in 1996, that is a very classic location to see a surface high pressure system in the case of these historic nor'easters across northern New England or just to the north of New York State, Vermont, and New Hampshire. So as I move forward here, that was the case in 96. You had this fresh intrusion of Arctic air. The storm system slowed down because in this case, there was actually a blocking pattern across the North Atlantic. And I believe I do touch on that right at the end of this presentation. With that blocking pattern, storm system slows down. So you get these incredible snowfall rates over a 10 to 24 hour period. And you can just get these monumental snowfall totals. In the case of 96, a wide band of 20 to 30 inches, in some cases up to 40 inches of snow in parts of West Virginia. I lived in York during this storm. I was very young at the time, only 4 years old. I still remember it to this day. We had 38 inches of snow officially at the York Airport in 1996. Just an absolutely monumental, kind of a historical type of benchmark type of system. I do want to switch over to a quick disco here because this is actually a clip from the Weather Channel from a broadcasting perspective. Some of you may know the name Mark Mancuso. This is actually a clip of him describing from a broadcasting perspective what some of the factors that are contributing to the 1996 storm development. So let me do that here really quickly. Here we go. All right, can everybody see that now?
Yep. Yeah. See that?
All right, I will play it.
I don't think we're getting sound.
No sound. Okay. Sound. That's strange. Can you hear it now?
I don't believe so. Let's see. If you
Shame.
maybe if you enter maybe theater mode, maybe if that might help.
Okay, let me see. Yeah, I don't know how to do that. Let's see. How about this? Computer audio. This might work. Share sound. Oh, here we go. Share sound. Share. How about now? Can you still hear me?
I can still hear you. Yep.
Okay, let's try it now.
The storm could slow down.
Mhm.
And if that happens,
Yep. So if you just share your
Sunday could get a
screen.
50.
Okay, perfect. That worked. Share. Not letting me share my screen. All right, here we go. This should work. How about now? Perfect. Okay.
Let's see. Oop, I don't think we have it again, but that's all right. If we keep going and look at the visual.
Sure. Yeah, that's fine. It seems like it's only letting me share sound or the screen, not both.
Got it.
Unfortunately. Yeah, I'll show you the visual. What he's talking about here is your upper level energy that's located up over the Ohio Valley. And there's a surface low on the coast. So think of the upper level energy is what I was showing you on the 500 millibar maps. The surface low, in essence, what he's saying is he's waiting for that upper energy, or the low is waiting for that upper energy to catch up with it and in essence capture it and cause it to stall out. Okay, I'll stop it there. Basically, what he was saying there is he was talking about how much precipitation there is on the radar and the fact that there could be a widespread 30 to 50 inch snow band with this with that system, in which in fact there was. And because it was such an impactful storm, he was talking about how there could be widespread power outages, impossible travel, get out to the stores, stock up on supplies, because it could be a while until you get out again. Again, 30, 50 inches of snow, that's a lot of snow, and it'll oftentimes make roads impassable for days on end. So with that, I'll jump back in here to the presentation.
Great,
So
thanks.
I'll go over a general forecasting tips and challenges here for nor'easters. What we want to do is we want to look for two pieces of energy that will either join forces, or what I like to call phasing, and what most forecasters will call phasing. The timing and location of this phasing is key, and it will also play a major role in determining where the heavy snow occurs. You want the surface low, like I mentioned, to stay out ahead of its upper level supporting energy, because the surface low is in essence waiting, or that upper level energy lagging behind the surface low will cause it to slow down. And the surface low is kind of waiting for that upper level energy or support to catch up to it. And oftentimes we as forecasters will talk about the upper level storm trying to capture the surface cyclone. And that's all we mean by that, is that the surface low is actually waiting for that best energy and lift in the atmosphere to catch up to it and get overhead, at which point the system bombs out and it deepens, snowfall rates intensify, and you have a bona fide nor'easter. Look at the big picture. Does the large scale weather pattern support rapid storm intensification on the East Coast? So this is where you have to look at your large scale teleconnections. So the state of the North Atlantic Oscillation, Pacific North American pattern, even the state of the Eastern Pacific Oscillation. So do you have a ridge axis over the Western United States, a trough in the Eastern United States, but unlike Clipper systems, you also want to look and see if we have blocking over Greenland and northeastern parts of Canada, or a negative NAO pattern. And we need that NAO to be west-based. When I talk about blocking over Greenland and northeastern parts of Canada, I'm talking about a west-based negative NAO. So again, that's looking at that big picture. And oftentimes the ridge axis in the west, you want the center of that ridge axis to be located very close to Boise, Idaho. That's an old rule in forecasting. If the ridge axis is located near Boise, Idaho, and you have a storm system moving up the East Coast, that's the perfect location to get a snowstorm just north and west, or even sometimes along the I-95 corridor. So if that ridge axis is within 50 to 100 miles either side of Boise, Idaho, you really got to be worried about a nor'easter if there's energy hitting the East Coast and a storm system moving northward along the coastline. Just a 50 and I-95 corridor oftentimes will be right on the line between rain and snow, or a wintry mix. So a 50-mile shift in storm track one way or another can mean the difference between rain and snow. And here in the Lancaster area, that plays into effect as well. Sometimes storm systems will shift 50 miles north at the last second. This actually happened here in December of 2020. Storm system shifted north at the last second. We were expecting a foot or more snow. We had about 8 or 9 inches of snow. The warmer air came in aloft the storm track farther north and west. We went over to sleet and freezing rain. We only had about 9 or 10 inches here in Millersville. So again, these little subtle shifts at the last second can mean the difference between a major snowstorm, a foot plus, or several inches of snow changing over to sleet and freezing rain. So track is key. Here's a near miss example. I wanted to show you a near miss example. This is in February 2013 to kind of illustrate what I mean with like the timing and location of that phasing. And again, I'm focusing this generally on southeastern PA here. So this was a miss for southeastern PA. You have this short wave, or this pocket of energy back over the Great Lakes region. You also have another disturbance down here off the Delmarva Peninsula. So you can see at this point, the two disturbances, they haven't merged forces yet. They're remaining separate from one another. And take a look at what the radar imagery looks like. You have precipitation associated with this surface low back up over the Great Lakes. And then you have more precipitation here off the east coast of the United States associated with that other disturbance. But they're still separate. You can see it looks disorganized. The areas of precipitation, they're not combined with one another. Light snow starting to move into southeastern New England, also parts of New York State. But look at what happens 12 hours later. Go back 12, go forward 12, and look at that. The two disturbances combined forces. So you can see that the northern branch piece of energy merged with the piece of energy out over the Atlantic Ocean. Take a look at that radar imagery and then look at what happens when the two pieces join forces. An explosion of snowfall. That's what happens when I mean by two pieces of energy linking up and joining forces. That low pressure system off the coast at this point has rapidly intensified. Snowfall rates have increased dramatically. And once the two pieces combine forces, you have this heavy snowfall band that sets up, again, about 100, 150 miles to the north and west of that surface low pressure system. This system delivered 30 to 40 inches of snow in parts of southeastern New England. And it was a boom scenario. You went from little snow, light precipitation, and it just exploded when those two pieces of energy combined forces. Now, again, that's the timing part of it, the location part. Look at where they combine forces. I'm located down here in southeastern PA, which is about right here. They combine forces off to the north and east of where we're located here in Millersville. You want them generally to combine forces either over your head or to your south and west. You don't want them to combine forces once they get to your north and east if you want to see a big snowstorm. Oftentimes we'll talk about the track of this upper level low pressure system indicated by this closed contour here that I'm highlighting over southeastern New England. If that contour tracks underneath of you, then you'll oftentimes get hit by the heaviest snowfall. But what I look for oftentimes is these contours starting to close off to my south and west. So here in southeastern PA, if I start seeing pieces of energy combined forces over the central Appalachians, western parts of the Carolinas, lower Ohio Valley, I'm starting to think, yeah, we could have a problem here. We could have a really big snowstorm. But in this case of like February 2013, if I don't see the pieces of energy combined forces until they're to my north and east, we're probably going to be left out. And the heaviest snow, at least in this case, would be off to our north and east. So that's what I mean by location and timing of when these systems combine forces. It's everything. Because if they combine forces north and east of you, you're pretty much out of the game for a historic snowfall. So here's your near miss example, and you can see it here in February of 2013. Once those systems combined forces over New York State and parts of New England, it was a major snowstorm, historic storm. I actually have a student here at Millersville that lives up in Connecticut, and she measured about 40 inches at her house. Whereas down here in Millersville, look at that, we had less than 4 inches of snow. It was a nuisance event. In fact, I think in this event, we had about 1.5 inches of snow. That was it. But once you get to New York City, points north and east, areas near and to the north and east where that system closed off, that's where you get your big snowfall totals. So here is a favorable nor'easter pattern. This is where I wanted to touch on that North Atlantic blocking. So I know there's a lot of colors here on this map. What this means, you're looking at 500 millibar height anomalies here. So I already described what these numbers mean, the numbers like 534, 531. That's the height of the 100 millibar pressure surface above the ground in decameters. Where you see these dark shaded red and blue areas, that represents how much higher or lower than normal the height of the 500 millibar pressure surface is in comparison to what is considered normal for that time of year. So in layman's terms, where you see these higher or these dark red shadings, that represents higher than normal 500 millibar heights, or represents areas where you see abnormally high pressure systems or warmer than normal conditions for that time of the year. So that's exactly what we have here. This would be a favorable nor'easter setup because we have that blocking over Greenland, northeastern parts of Canada, such that when you have these storm systems hit the East Coast, it acts to slow them down. You can kind of see here that the pattern, it gets disjointed over southern Canada, northeastern parts of the US. You've got these lines going in all kind of different directions. That basically means the storm system is slowing down. So that's what we look for a favorable nor'easter pattern. If you see lower than normal 500 millibar heights up here over Greenland, that's not favorable. That means we don't have a lack of blocking. It's a very progressive and fast weather pattern, and it won't be favorable for nor'easters. So, and there you go. That's what I'm showing, the unfavorable nor'easter pattern. You've got this very fast flow on the East Coast, up here over Eastern Canada and parts of the Northeast. Very fast flow there. The storm systems don't have a chance to slow down on the East Coast, and you're left with, more significant or moderate snowfalls on the order of 4 to 8, 6 to 10 inches. That can still happen in these cases, but in more times than not, you're not going to get the big historic nor'easters when you don't have blocking over Greenland. So that's where I am with nor'easters. Questions?
All right, we got 2 submitted right now. Richard asks, what is the, oh, no, sorry, it just got answered. But the question was, what is the mechanism that causes the surface low to slow while the upper level catches up? Which just got answered. James asks, what's your forecast for Friday's storm? Would you call it a Colorado low?
Yeah, I'll answer the first one first. Well, it's really that essence of that blocking. Let me go back here on the slide. If you see what happens, the flow here across the western and central United States, it's really fast. You can see that these darker lines are very tightly packed close to one another. But look what happens when you get out here over southeastern Canada. They're not as tightly packed. Here over the East Coast, they're not as tightly packed. It looks like they're tightly packed up here, but again, this is a disjointed weather pattern. So it's almost, think of these as semi-permanent features in a blocking pattern. They're not really going anywhere. So this looks like it's going somewhere, and it is right now. But once it hits the East Coast, it's going to slow down because those other 2 features are locked in. So that's in essence what causes the entire both upper level and the surface low pressure system oftentimes to slow down, is just the effects of that strong blocking in areas downstream from the winter storms. And then as far as the system coming up, yeah, I haven't actually, really looked at areas farther to my west. We're having enough of a nightmare with it here in southeastern PA. Where's your location? Like, curious for a forecast. If I could get where your location is, maybe I could give you an idea of what to expect.
James can answer that in the chat. In the meantime, would you be able to take one question from Bruce?
Sure.
Oh, James says Nova Scotia.
Oh boy, yeah, I haven't looked at Nova Scotia right now. No, I'm sorry, I can't give you a really good forecast for Nova Scotia because I haven't looked into it.
So Bruce asks, if I recall, Uccellini's and Cochin's treatise, they found very few cases where nor'easter did not involve the formation of a secondary low as the overall system tracked to the northeast. One that comes to mind in my recollection is the storm of the century in March 93. Another I can remember without secondary low formation and intensification is the blizzard of 66, which is January 30 to 31, 1966. I guess I'm saying, using your terminology, Miller type 2 is much more frequent for East Coast than East Coast snowstorms. Your thoughts?
Miller type 2, is that Miller A or Miller B?
I think he says B.
Miller B.
Let's see. So let's see. Yeah, Miller B.
Miller B. Miller B, yeah. Miller in general, it depends. Well, first you got to look at the state of La Nina and El Nino. If you're in an El Nino type winter, oftentimes you'll have more southern or more energy associated with the southern branch of the jet stream. You have a stronger southern branch of the jet. Oftentimes you'll have storm systems crashing into the Pacific Northwest or California. They move across the Rockies, tap into that Gulf moisture, and it's just one storm system the entire way. So Miller A's are much more common in El Nino winters. In La Nina winters, like what we're in right now, they're much less common. You're more times than not, you're going to see Miller B's because you have a northern branch dominant jet stream in La Nina patterns. And that's what we've seen all winter long. We have these disturbances coming out of the northern branch of the jet. The energy associated with the southern branch is weak. The 2 branches of the jet stream are very far apart from one another. So that's a Miller B setup where you have 2 different pieces of energy trying to interact with each other. Oftentimes they won't phase in time to produce big storms on the East Coast. We've seen that a couple of times this year. We have seen a case where it did at the end of January, a piece in the southern part of the jet phased with a piece in the northern branch of the jet. And again, that ended up being a historic nor'easter for parts of the Jersey coast. But again, more times than not in El Nino, Miller A's will be more common than Miller B's. But in La Ninas or years where we really have a neutral signal, from El Nino and La Nina, meaning that neither one are in their active phase and so is inactive, you'll get Miller B type storms to be more common.
All right, thanks.
Mhm.
Do you have time for one more question, or we might be a little bit over, but I want to be respectful of your time.
Yeah, I actually have a few more slides if you want me to take a few more at the end. This won't take too long.
All right, we can just run through these. Yep.
Okay, sure. All right, I'll run through a couple more of these slides. I'll skip this one. This was actually back on January 3rd. I'll explain what happened and why forecasting is so difficult and why you kind of need us here as forecasters, because we look at a conglomeration of different computer models, 5, 6, 7 different models at once, and they can change drastically from run to run. So I'm not actually going to play the loop here on account of time, but this was the European model. You may recall back on January 3rd, that surprise snowstorm that crept up in parts of Virginia, southern Maryland, southern New Jersey, and Delaware led to that chaotic mess on I-95 where people were stranded on the interstate for 24 hours at a time. This was the European model for that storm, 72 hours before it hit. Actually 66 hours there as I'm looking on the top left. That's a 66-hour forecast from the Euro. And this was for the exact same time when parts of Northern Virginia got 12 to 15 inches of snow. That's less than a 3-day forecast right there. It's got no snow anywhere in the mid-Atlantic. And if I were able to play the loop, you'd see this progressively run by run shift 50 miles north and west, each run at the last second. So this is model mayhem. Models can jump drastically in their suggested outcomes from one run to another. So that's why it's so important to hone in on the upper level pattern. Make use of these past storms. Look at the large scale pattern. Look at what they produced in the past, because weather in the past oftentimes will give you clues to forecasting weather in the future. So I cannot stress the impact of being able to go back to some of these past storm systems and seeing what they did and what the pattern looked like. Because if the models are not matching up oftentimes with prior instances of these storms, oftentimes there's something wrong with the model. Quick glance over here of snow, sleet, or freezing rain in determining precipitation type. If the air from the surface to the top of the atmosphere is below freezing, throughout the entire depth of the atmosphere, you're going to see snow. If you have a narrow layer of warm air aloft, you'll actually have some of those snowflakes melt and then refreeze before hitting the ground. That's when you get your sleet. If this warm layer aloft is deep enough, those raindrops won't have a chance to refreeze until they hit the surface. So freezing rain is simply just plain rain that then freezes on contact with colder objects such as trees, paved surfaces, power lines near the ground. And then plain rain obviously is when temperatures are above freezing, generally throughout the depth of the atmosphere. Snow, sleet, or freezing rain. This will kind of touch on that question related to this storm system. It's not for Nova Scotia, but I'm pulling up a couple of model soundings here. I'm not going to go into in depth what a sounding is, but it's basically a vertical depiction of how temperature and dew point change with height in the atmosphere. Numbers on the left here represent different pressure levels. You're going up in height through the atmosphere. Temperatures here on the bottom in increments of 10 degrees Celsius. So this is your freezing line right here, your 0 degree temperature contour. What do you think would happen in this case, sleet or freezing rain? Well, I'll give you the answer. It's freezing rain. You've got this deep layer of warm air right above the surface, but look at your surface temperature. It's 29. So you're going to have snowflakes melting here, turning into raindrops, and they're not going to refreeze until they hit the surface. But this sounding here would suggest sleet. Snowflakes will melt and turn into raindrops in this narrow area of warm air aloft, but they'll have plenty of time to refreeze before they hit the surface. So that's a sleet sounding right there. So again, depth of that warm layer is very important in forecasting sleet versus freezing rain. Freezing rain makes driving nearly impossible. It's more treacherous than even snowfall will be. Tires can't gain traction at all on icy roadways. Freezing rain followed by snow is much worse than snow followed by freezing rain, because if you have snow on top of ice, your tires are going to be hitting that icy layer. They won't be able to gain traction at all. Whereas if you have snow and then ice on top of it, the tires are going to be feeling the effects of that snow more so than the ice. So it's always worse to have ice to snow than it is to have a snow changing to ice event. Again, people tend to panic in icy conditions. If they lose control of their vehicle, they'll be slamming on their brakes. That's not going to keep your car from spinning out. In fact, it's only going to enhance that spin out. You want to gently tap the brakes and remain calm in instances like that. So again, here's a couple of conclusions and takeaways, and then I'll be done. Winter weather forecasting, it'll never be an exact science. Forecasting models will never be perfect. They're based on approximations. They're All the equations of motion in the atmosphere are based on approximations, and they're then fed into the models. So the models will never be perfect. Our job as meteorologists is to use pattern recognition and knowledge of past storms to give the public advanced lead times and the most accurate forecast possible. And then you also want to convey the impacts to travel, life, and property. You can put out the most accurate forecast on Earth, but if you're not conveying the impacts to society, the forecast may virtually be useless because people aren't going to know how to respond with the forecast information that you've given them. Snowfall rates and arrival and times of wintry precipitation matter just as much, if not more, than total snowfall forecast, because it's oftentimes, if say you're predicting an arrival time of snow at 7 p.m. after the evening commute, what happens if that snow arrives at 3 or 4 p.m.? Then people that think they're going to have an easy evening commute, dry roadways, all of a sudden go out in slick roadways, snow-covered roadways, low visibility, and you could have a completely, totally nightmare situation in comparison than if you forecasted the arrival time and the snow arrived after the evening rush hour. So that's just an example why arrival and end times are very important. So people know how to properly prepare and what kind of road conditions to expect. Salt and road treatment chemicals become ineffective below approximately 15 degrees Fahrenheit. So unfortunately, if you have a major winter storm occurring and you're in the low teens or high single digits, those salt and treatment chemicals become much less effective. Stock up on supplies and batteries before a major winter storm. And if you're ever going to travel in a winter storm, basically think back to the situation that happened on January 3rd. People were stranded in their cars for up to 24 hours. So if you do have to travel, if you do plan on traveling on the roadways, you never know when you may run into a multi-vehicle pileup. So if you have to do that, pack extra food, pack extra blankets, just in case you encounter one of those situations, because the last thing you want to do is be stranded on a highway, run out of gas with temperatures outside of your car in the teens, and not have blankets, food, or water to see you through the situation. So I think I'll end there.
All right, Kyle, thank you so much for the presentation today. Really appreciate your time, and thank you all to everyone who is watching and contributing. If you have more questions, feel free to post them on the Weatherband community. I'm going to try and keep an eye on those. And Kyle, I can send them over to you to get them answered.
Yeah, that sounds good to me, Eric.
Thank you all very much for a fantastic webinar today.
Yeah, thank you, Eric. Appreciate it. Thanks, everyone.